Example problem 687. For the shearing mechanism in the configuration shown, use the instantaneous center method to analytically determine the linear velocity of the blade as the crank rotates clockwise at 55 RPM. Okay, so the first thing we're going to do, let's go ahead, let's draw a kinematic diagram, and then let's get a couple. We don't need all the instantaneous centers, but we're going to need a couple instantaneous centers to solve this problem. So go ahead and draw, just get that. Okay, draw this shear down here, maybe use the shape. All right, let's label some of these joints, draw our frame connection. A, call that B, and we'll call this C down here. Okay, so let's label a couple angles just real quick. So that's theta 2, because we'll call this, actually we'll call this length 2, we'll call this length 3, we'll call this length 4, and we'll call length 1 out here. And then we'll label another angle. We'll label that theta 3. Okay. So we have these done. We can go ahead and we can label these instantaneous centers that readily jump out at us. Right up here would be instantaneous center 1, 2. We have instantaneous center 2, 3 down here. We have instantaneous center 3, 4 here. So another instantaneous center that we're probably going to want is 1, 3. So to find 1, 3, the simplest thing to do would be to know that an instantaneous center from 3, 4, or from point C rather, we'll draw perpendicular. Let's use this color. It'll be perpendicular off of this slide joint. And we also have, right, using Kennedy's theorem, we have two instantaneous centers here, 1, 2, and 2, 3. So we know that the instantaneous center 1, 3 is going to be in a straight line based off of those, and we get a nice intersection point, and we'll call this point D, but it's the instantaneous center 1, 3. Okay, so we have that. So now let's start looking how we might need to go about solving this. So the first thing, one of the easiest things to do, we can go ahead and let's solve for theta 3. And that's fairly simple. We're given a formula for this, for an offset solder crank. So theta 3 is equal to the sine inverse of L1 plus L2 times the sine of theta 2. All of that is over L3. Now, since this is an offset slider crank, L1 is that offset distance, and we're given that offset distance, it's 1/2 inch. So we can go ahead and we can plug some numbers into this. So sine inverse of L1, 0.5, plus L2, which is 0.75, times the sine of theta 2. Now, up here in the figure, they give us that length 2 is 40 degrees off of the horizontal, so theta 2 is 50 degrees. 50 degrees. and that's divided by L3, which we're given as 4 inches. And with that, we get theta 3 equal to 15.58 degrees. All right, now it's probably reasonable that we'll want to, we're given the crank angular velocity in RPM, but we're going to want that in radians per second. So if we're going to put it in an equation, you should know by now we need it in radians per second. So we can go ahead, we'll just do it up here. Omega 2 is equal to 55 RPM, and this is times pi over 30 to put us into radians per second. So omega 2 is equal to 5.76 radians per second. Okay. Now that we have our omega 2, we can easily find the velocity at B. So the velocity at B, right, we just draw this on the figure real quick here. The velocity at B is perpendicular to link 2, right, because link 2 is rotating around point A, so we have a velocity VB. And VB is easy enough to solve. It's equal to omega 2 times L2, and this is equal, so 5.76 radians per second multiplied by link 2, which is 0.75 inches, and that gives us 4.32 inches per second. Okay, so now we went through the effort of finding our instantaneous center 1-3. We might see how we might start to try and lay this out here, but first what we're going to do is we'll probably need to go ahead and figure out what the length AD is, and that should be simple enough. So how we're going to go about this is, well, we know this angle theta 2, we know this angle theta 3, and we know these two lengths. So we can get the vertical distance between point A and point C, right? This vertical distance. And since we'll know that vertical distance, and we'll know the angle that the line AD makes with the vertical, we can easily solve for the total length of AD. So let's go ahead and let's write that out. So AD is equal to AB times the cosine of theta 2 plus BC times the cosine of theta 3. And this is over, right, because that gives us our vertical length. That gives us this vertical length here. And if this vertical length is equal to AD times the cosine of theta 2, well, then we can just divide by the cosine of theta 2. And we'll go ahead and we'll plug numbers in for this. So AB is 0.75 inches times the cosine of 50 degrees plus 4 inches times the cosine of 15.58 degrees and that is over top of the cosine of 50 degrees, and this gives us the length AD equal to 6.75 inches, and which real easily, right, we can see length 2 is 3/4 of an inch, so BD is equal to 6 inches. Okay, so the next thing, so what we're trying to look for, right, again, is the linear velocity of the shear, or the linear velocity of point C as it moves along that slide joint. So how are we going to go about doing that? Well, we have this instantaneous center, 1, 3. And we have a velocity at B. And since we have a velocity at B, we can find omega 3, right? We can find, it's easy enough to where we can say that omega 3 is equal to the velocity at B divided by BD. And all we're doing is we're shifting our equation around, right? We just solved for the velocity of B, right? Velocity of B was equal to omega L2. But we know, right, we know at point D, that is an instantaneous center of rotation, right, as we're observing from link 1, we're observing link 3. So it looks like link 3 is in pure rotation, so we can treat it as though it's pure rotation. So if we know, right, the linear velocity at B, then we can easily find our omega, that link 3 is rotating, right, appears to be instantaneously rotating around our point D, or instantaneous center 1, 3. So let's go ahead and solve this. So the velocity of B, we already found 4.32 inches per second, and that's divided by BD, which we found to be 6 inches. And this gives us omega 3 equal to 0.72 radians per second. Okay, so now we have the rotation, right? We have omega 3 as it's seen, right, about its instantaneous center, 0.13. Well, now all we need to do is we need to find the length, CD, and we can go ahead and use our simple velocity equation again and find the velocity of point C. So if we're looking to solve for CD, well, we're given actually this horizontal distance, right? This offset distance of this offset slider is 1/2 inch. And then all we have to do is find this horizontal distance that BD covers, and that's simple enough, right? Because we have theta 2, so we know the angle. So CD is equal to 0.5 inches plus BD times the sine of theta 2. So 0.5 inches plus BD, 6 inches, times the sine of 50 degrees. CD is equal to 5.67 inches. And so the velocity at 3,4, at the instantaneous center 3,4, is equal to omega 3 multiplied by CD. So omega 3, 0.72 radians per second, multiplied by CD, 5.67 inches, gives us the velocity of the shear is equal to 4.08 inches per second.